Hello students, welcome. So here is a problem, one more problem on work energy principle. And please note that as I said, even if the diagram associated with the problem appear complex, the solution is very simple. So all the problems in work energy principle basically they are very simple. All that you have to do is start with writing the general energy equation, that is energy balance equation one can say. And here we will do that. Let's read the problem. So a problem here is that there is a 1.5 kg collar which is attached to a spring and slides without friction along a circular rod in a horizontal plane. The spring has an undeformed length of 150 mm and a constant K, that is spring constant, which is equal to 400 newtons per meter. Knowing that the collar is in equilibrium at A and is given a slight push to get moving, determine the velocity of the collar as it passes point B, right? So velocity at point B, this is what you are asked. Now here please note that as I said, we will begin by writing a general equation of energy equation between points A and B. The collar is first position is A and the second position is B. So what we will say is that energy at A plus any work done on this collar, right, by external force minus frictional energy lost in friction will be equal to energy at B. So this is what the expression. We'll write a general expression and then put the values. We might want to strike out certain energy terms, but let's start from writing a general expression. Okay, so I'll write a general expression here. So see, I'm writing between A and B. So I'll write first. I'll say at A there is some spring. So I'll write half K1 x square, that is spring energy, plus I would say that there could be potential energy, plus there could be kinetic energy, plus some work done by the external force minus some frictional energy which is eaten away by frictional force. This is equal to energy at point B, and energy at point can also be spring energy. So K2 x2 square. It can also have potential energy mgh2 plus it can have some kinetic energy mv2 square. Now this expression, general expression, which you all always remember, and you don't have to we don't have to memorize it. You can immediately logically construct it, and you know how to do that. If you I have elaborated this in the previous example also. I think this is a fifth or I think it's fifth or fourth. I think fifth. So go back to fourth and example numerical, and at the beginning I just explain each term and write this equation. Okay, now we are talking about A and B. Now see this rod, circular rod on which the collar is rotating or sliding, right? This circular rod is placed horizontally. Just see this. Look at this. Circular rod in a horizontal plane. What does it mean? It means A and B are at the same level. And it means, automatically it means that, and this is equations we have written, this part of the equation is for position A. This part of the equation is for position B. If A and B are at the same level, we can immediately say that the potential energy of this collar when it is at A and when it is at B, it can be, you can see, when it is at A and when it is at B, this will be same. So we can strike out the potential energy, right? So we can say, we can say that the potential energy is wait a second, I'm just some problem here. Okay, so the potential energy terms from both the sides can be cancelled out. So this is cancelled out, right? This is cancelled out. And what about spring energy? Well, there is spring. See, from H, see the point H to collar, that's the entire length is of spring. When the collar is at A, then H to A is the entire length of the spring. H to B is entire length of spring. So there is spring energy. We'll come to that. You also know that at A, it starts from A. So V1, the velocity at A, which we called it as V1, will be 0. So the kinetic energy will be 0. Similarly, look at the collar. Is there any external force acting on it? There is no external force acting on it. The spring will be pulling it and all that, but external force, that is any separate force, that is not there. So work done is also gone, right? F into D. Also, you are told that there is no friction, right? That the diagram says that, the description says that there is no friction. So this energy is also gone, right? So what you have is basically half K1 x1 square is equal to half K2 x2 square plus half m v2 square, right? So this is what we have, and what we want to find out is v2. We want to find out v2. Now look at K1, K2. Now it's the same spring, right? At A also it's the same spring, at B also it is the same spring, and so K1 and K2 are same, and we are given the value of K1 and K2 is 400 newtons per meter. Okay, 400 newtons per meter. Now what we have to do is K1 is equal to K2 is equal to 400. We want to find out x1 and x2. So if you find out in this equation, K1 is known, K2 is also known, they are same. As I said, it's 400 newtons per meter. Then mass of the collar is given is 1.5 kg, right? It is 1.5 kg, you can see 1.5 kg collar. So that is also known. So this equation, so in this equation, if you find out x1 and x2, you should be able to find out v2 square, and from there you will find out v2. Now let's find out x1 and x2. Now see, x1 means x1 is what? x1 is the deflection of the spring when it is at position A. Now see, to find out x1, let's find out the length of the spring when it is at position A, and you can immediately find out. That means we'll call this as original length. No, it's not original. We can say original is given, right? What is the undeformed length of the spring? Undeformed length of the spring, as you can see here, is 150 mm, right? 150 mm is undeformed length. So when the collar is at A, you can say that the total length of the spring at A, total length is equal to, you can see at A, it is HC plus CA. HC plus CA. So HC is how much? 175. CA is how much? 2 into 125 is radius in a way of that circle. So 2 into 125 is CA, right? So it is 175 plus 250, 175 plus 250, and that is going to be 425 mm, right? 425 mm, which means length HA is length of the spring when it is at position A. But the original length of spring when it is undeformed is 150. So at A, the spring length is more than 150. By how much? The spring length is more than 150. By how much? So we can say that is nothing but the extension of spring, right? Deformation of spring, stretching of spring, and this is our x1. And because the spring is stretched at A, the collar has energy, which is spring energy, which is given by half k1 x1 square. So x1 is the stretch, or the how much it is elongated. So that is going to be 425 minus original length, LO, right? And 425, sorry, 425 minus 150, right? 425 minus 150. So this is your length, and this is going to be it's 5, 7 and 275 mm. Okay, it is 275 mm. Now this is x1. Now can we similarly find out x2? To find out x2 is what? x2 is the compression or deformation, we can say, of the spring. Deformation is not the correct word. We can say it is the stretching or compression, right? If the spring could be stretched or compression, deflection is the correct word. What is the deflection of spring at point B? We have found out deflection of spring at point A. Now we find out deflection of spring at point B. Okay. To find out deflection of spring at point B, look at this. Now the spring is connected between H and B. Okay, between H and B. Please note, collar is coming at B, so the spring length will be HB. At B, the spring length is equal to HB. Now, how would you find out HB? Just see, HB is, if you see, it's you have to use Pythagoras theorem. So you know this is, I'm drawing this here. Sorry, I need to draw it correctly. Okay, so here it is O, here it is B, and here it is H, right? So we can write HO. HO is how much? It is HC plus CO. Please note that it is HC plus CO. And what is HC? 175. What is CO? 125, right? 175 plus 125, that is HO, and this will be 300. Sorry, 300. And what about OB? OB is, radius of that circle, so it is 125. So you can find out HB by using Pythagoras theorem, and this is a root of 300 square plus 125 square, and this will be HB will be, let me give you the direct answer. This should be 325 mm. 325 mm, right? So we have found out. Now this is HB. Am I right? This is HB. But we want to find out, and we know that the original length of the spring is 150, and the length of the spring when the collar is at B is 325. So what is the deflection of the spring? What is the deflection? X2 deflection at B. Deflection at B is X2 is equal to original length, right? So, or rather here I can say it is 325 minus original length. So it is 325 minus 150, and this will be equal to 175 mm. So please note, our x1 is 275 mm and x2 is 175 mm, right? If we have x1 to 275 here, x1, and x2 is 175. Okay, now let me clean it and we will substitute the values. Okay, so, or we can do it here also, that's not a big issue. Okay, let me. So this is, I'm cleaning it all, and this is our equation, right? And in this equation we are going to write the values of x1 and x2. So now please note that x1 is in mm, so we convert that into meters, because why? Because K, stiffness, is in newtons per meter, so we convert that mm into meters. So this is 275 mm is equal to 275 by 1000 meters, which is 0.275 meters. This is x1. And similarly you can say x2, you can say x2 is 175 by 1000. This is 0.175 meters. Okay, so we have now 0.275 and 0.175, and now these values are to be substituted in this equation, which I will underline with blue color. This is our equation. We have found out x1 and x2. We also know the value of value of K. So we can substitute the value. So we can say, let me go back to black. So I'm writing this half m v2 square is equal to half K, and let's find out what is K. K is 400, right? So K is 400, half into 400 into, I'll write x1 square. X1 square is 0.275 square minus x2 square is 0.175 square, right? So if you solve this, and you know m, what is m? M is mass of the collar, which is 1.5. So you could substitute over here. I'll just clean this all. Okay, so this is done. Okay, so again we write, then here half gets cancelled, then you can say 1.5 is mass v square is equal to 400 into bracket 0.275 square minus 0.175 square, right? And if you do the calculation, I'll leave it to you. And I think V, actually it is V is at point B, right? And I'm just picking it, answer is I'm picking from the book. I'm not doing the calculation, but I think it should be okay. It's the correct answer, and this answer is 3.46 meters per second. Please note, it's such simple problem, just one equation. This is all, this is all we have written. These are the 4 steps. This is what you have to remember. You have to remember the first equation and everything is done, right? Okay, thank you.